So you're designing an edge device, are you? Well, before you get too far along in that design concept, we should address the giant elephant in the room. No, not your caffeine intake, which has been a bit much lately. Yes, I have noticed. Maybe you should cut back a tad? Maybe? No, I'm talking about security. Wouldn't it be nice if there was some kind of security solution store for your next IoT edge device? You know, like one of those auto parts stores that seem to be in every town in the United States? You know, like AutoZone? Maybe we could call it Security Zone. And no matter what kind of malicious attack, IP thievery, denial of service, or data theft, you could just find the right aisle. Let's see. Cloning issues. Yep, that's on aisle 4 on the right. Wouldn't that be nice? Hi, I'm Amelia Dalton, host of Chalk Talk. Maybe we shouldn't go into the brick and mortar security parts business, but having our T's crossed and our I's dotted in our next IoT edge security plan, that sure would be nice. And maybe we can. In this episode of Chalk Talk, Brendon Slade is here to introduce us to the powerful new LPC5500 series of MCUs from NXP. Not only do they pack a serious performance punch with not one but two Arm Core processors, they also have that whole security thing covered. All right, let's go. And before we get started, don't forget to click that link. There you can find even more information about the LPC5500 series of MCUs from NXP. Hey, Brendon, thank you so much for joining me.
Great to see you again, Amelia.
Okay, so we are here to talk about the LPC5500 with ARM v8M, which sounds super cool. But Brendon, I know it's going to be a bit of a leap from my Cortex M4 design, right?
Yeah, sure, but it's not as bad a leap as you might think.
Phew, okay.
But there's a lot of good things that come along with making that leap.
Excellent.
So if you look at this slide here, we can see the Cortex M4 on the left-hand side here, but you can see all the nice green goodies that ARM have added on the Cortex M33. So there's various enhancements and so on and so forth, but one of the key things is now you can issue up to 2 instructions per cycle. If we look at industry standard benchmarks like TrustZone MIPS per megahertz and core marks per megahertz, you can see you get up to about 20% performance bump in terms of TrustZone MIPS. And along with that native core execution, there's also the possibility for enhancements that ARM have enabled. So they have a coprocessor interface, and you can put more than one coprocessor onto that and really boost up performance. And NXP's done that with its Powerquad DSP and also its Casper crypto accelerator that's in this particular series. And then TrustZone is another key part of ARM v8M, and that's all about security. And I'm sure you've got some questions for me about that.
Oh, I absolutely do. So this sounds really cool, and it seems like you guys have crafted some really clever stuff around this.
We like to call it our special sauce. I'm sure our engineers are going to hate me for this picture because it looks a bit scummy, but some sauces are a little bit like that, right?
They are, true.
Yeah. But we do think, we've created some really nice things based on that new core from ARM. So one of the key things we've done is put 2 cores into this series. So there's a primary and secondary core here.
Okay, so Brendon, 2 cores. Hold on a second. What's the difference between these two, and which jobs are allotted to which one?
One of the cores we've basically maxed out, right? It's the top-end model with everything enabled and turned on, and it has that DSP coprocessor, the crypto coprocessor. And the other one is really the opposite end. So it has the vectored interrupt controller, but it doesn't have all those other things, which would add area which means cost, and power, of course, as well. So the secondary core is really there for system-level tasks, where the primary core has got all the grunt to do the heavy lifting, and it has the security aspects as well. So in order to make that work well, we've got a very efficient partitioning in the system, and that really is built by a multi-layered bus system. So then we enable DMAs in the different cores to access all the different facilities in the chip without colliding with each other, no contention. And there are several slave ports on these different devices in the system, so multiple masters can access them. And then the independent asynchronous timing information is really about optimizing the system power.
This is all great, but Brendon, tell me more about those coprocessors. What does that really buy me as an engineer?
Yeah, that's exciting, right? Sounds interesting and new. So if you look at Cortex-M MCUs, they were designed fundamentally for always-on systems where power is a big concern. Good integration and low power. But what we're seeing is when you get into these IoT applications, you need more performance. And this can come into different kinds of analytical things like MLAI applications, but also a lot of other applications too. As good as the Cortex-M processors are, there are cases where they just don't have the performance. So you'd have to move up to, say, an M7 core to get more performance, but that's going to cost you a bit more in power. So by having a coprocessor like this, we can get a lot more performance with a good energy footprint.
Okay, so let's talk a little bit about that DSP. Now, that's pretty difficult, right? I'm not big expert on DSP.
DSPs do worry people because DSPs typically are all different from each other, and you need a lot of expertise to really get the best out of them. However, Arm did implement this part of their CMSIS standards. They did implement a DSP API some years ago, and that's available for all the Cortex-M processors so that you can write very portable DSP code. And we harness that in order to give an interface into this DSP code processor. So you're programming at C level using potentially libraries that you already have for SimSys DSP. If you want to get more hardcore with it, you can do that as well. But most people can utilize that and get a lot of performance. I wanted to just show the picture here with all the different pieces that are there. So there's some engines like FFT engines and so on. There's also some matrix manipulation engines. There's hyperbolic and trigonometric functions, and also some signal processing standard pieces like FIRs, and then transcendental functions as well. So things that are quite easy to understand and kind of at a macro level, if you like, for ease of use.
Okay, so Brendon, what's the performance story here?
What do you get,
is this?
right?
All right. What does this really give me?
I'm spinning a good story, but what does it really mean? This next slide shows some of the typical kind of performance boosts you're going to get. So the table at the top there is using SimSys DSP API calls.
Okay.
So the M33 column there is what you get on a highly optimized C code on the M33 native. And then the next column is in terms of processor cycles. And the one PQ cycles, PQ for Powerquad, is showing how many cycles the Powerquad takes. So then you can see a simple ratio. So in some cases, the performance for a very small operation is good, doubles good, right? In other ones like the FFT, you see a very, very big speed up. And then the table below is things that aren't DSP functions as such, so mathematical functions, but then also the performance is very significant as well.
Sure. Okay, so what about power, Brendon? What's the story here?
Yeah, I'm not hiding anything from you. The 5500 series is built on 40 nanometer technology, so that gives you a great dynamic power story, also gives us more memory. But one of the other key things about power on this device is it has a built-in DC-DC converter. So we can drop that core voltage inside very, very efficiently rather than just dumping it on a regulator outside the chip. And by integrating it, also, it's saving board area and cost versus an external DC-DC converter. So that inherently gives a big benefit to us in terms of dynamic performance for current consumption, and that's the active mode, 32 microamps per megahertz. If you do a quick bit of math, you see that's about 3 milliamps for 100 megahertz operation, which is pretty impressive. And then we have these other modes for where you're going in and out of sleep modes when you're active or not active. Right down to the deep power down mode when the part is in a pretty quiescent state, but that goes below 1 microamp, meaning that you've got a part that sat there for years and years and years on a very small battery. So yeah, there's a lot of scope for very, very optimal low power operation.
Excellent. All right, Brendon, let's talk about the scary elephant in the room, security.
Yeah.
But let's first step back a second. And what kind of security attacks are you seeing today, and how can we go about stopping them?
Yeah, sure. Of course, security is a very broad topic.
It is.
We haven't got enough time, unfortunately. As much as I like spending time with you, Amelia, we haven't got time. Talk wouldn't quite cover it, right?
No.
So I kind of broken this down into a couple of different areas, if you like. So there's what I call production attacks. This is where people are basically trying to copy your product in one way or another. And unfortunately, there are untrustable CMs out there that would make more of your boxes, your products, than you really want them to, and they make their way into the grey market that way.
Yeah.
There are others where people want to snoop in on what your product does, just copy the whole board design, steal your firmware, and then make those under copying your brand or maybe under a different gray market brand. And then there's also if your CM is perfectly honest but gets duped with a fake MCU. So you think you got an LPC5500 series part, but you really don't. And that compromises your product. So there's those kind of areas.
Okay, that's great, but now I can stop people from copying my product, but what if it's already out there in the world? What can I do then?
Yeah, so worrying about your reputation, right? Or your
Exactly.
customers getting their information stolen and so on.
Yeah.
Of course. Then this is where most people think the key problems of security are in many cases, right? So there's different forms of attack and there's different intent of the attacker and trying to represent this, what is a very complicated picture in this simple diagram. Things like IP theft. So they get your product and they're trying to hack in and steal your software. Some of that could come back to the example we saw before where people are trying to copy your product.
Sure.
Maybe they're trying to evolve it into something else, a bit more sophisticated IP theft. There's data theft, right? So people trying to get banking information or biometric information or system secrets, keys, Wi-Fi, passwords, things like that. And then there's denial of service type attacks or other system integrity attacks, trying to hack something so you can unlock. One of the nice things about TrustZone is you could have premium features that you can unlock remotely. People trying to hack in and unlock the premium features like hacking HBO on cable systems, kind of analogous to that, right? Some of these things can cross the boundaries between these different things. And the circles in the middle are trying to show the kind of things people are trying to get access to. So they're trying to access the firmware. So they're trying to unlock those updates and those upgrades, rather, premium features and so on. Or they're trying to attack the firmware in order to enable a data theft or to enable a denial of service attack. Then you've got the actual information, again, keys and certificates that can also feed back into your firmware update. So if they're trying to hack your keys or your certificates so that they can enable a malicious firmware update. And then you have network integrity. So this is accessing the network. And again, that can be done through messing with your firmware, which can be enabled through attacking your keys and your certificates. So all of the things are intertwined. So people get worried because they think, oh my gosh, I've got to think about absolutely everything here. And it's overwhelming. Whereas it may be that you want to look at it and say, well, how much is good enough for what I need? What do I really care about? And what are the real attack surfaces of my product?
Right.
Something like an e-meter is probably the toughest case because people would be motivated to go in and hack one meter so that they can then fix their own electricity bill.
Right.
Things like that. Also, in those kind of cases, you want to prevent one break, then breaks everything else attacks. So somewhere like an e-meter, you may need things like a secure element, things to make it tamper-proof and so on and so forth. So there is a spectrum, but the LPC5500 series covers this spectrum very well. It's going to solve the problem for most customers.
Okay, Brendon, that sounds great in theory, but how exactly are we going to go about doing that?
The key thing here really is isolating the security-related functions from the rest of the application. So that's a very good way to protect yourself from attacks. A cornerstone of that is TrustZone, but there's also all these other aspects to a secure execution environment. So if I just run down this list here, so we have secure isolation. That's separating your secure and non-secure worlds. Booting securely. So you making sure the software you're running is legit, right? Is it the real thing? Is it hacked or is it what I should be running? Having secure primitives so you can efficiently do things like encryption and hashing and so on so that you're efficient. So if your product is so slow trying to connect and everything, that's no good. It's not going to meet the customer's requirements. Secure storage. So you have keys and certificates to enable these other things. You need to be able to securely store and manage those. Being able to do a secure update. And if your product's an IT product, it's remote connected, so you have to be able to update the software remotely. And then secure debug adds a nice layer to this in that you can potentially have different levels of debugability at different stages of the life cycle of the product.
Sure. Okay. So where does TrustZone fit into all of this?
Yeah, TrustZone is about the secure isolation. So if we look at the picture here, you have this notion of an untrusted and a trusted part of the processor, but it's really just one processor. And it does that by having access to the particular areas only enabled when you're running in secure or non-secure mode. And the examples we see here are, say, root of trust applications. So you have the cryptography, the secure system, secure storage, random number generator, then trusted hardware, trusted software. So that's a root of trust application. Everything's trusted from the bottom to the top. IP protection. So locking down valuable IP inside of that trusted region, again, on top of trusted hardware and drivers. So there's no loophole through a driver or some hardware to get into that software. Sandboxing, this can be security or may not be. Say, for example, you have a radio that you've gone through certification and that's kind of locked down and certified. If you mess with that software, you can break your certification. So
Sure.
you keep that secure. And then the 5500 adds on top of these. So it adds some attribution units onto the standard core attribution. And that the attribution is what defines is secure or not secure. So outside of the core, it does that into the rest of the system. And it adds this second factor of protection by having bus checkers. So even if the core software says this is the right enablement, through some malware or hacking, the software may be forced to try and do some roundabout access. So by matching up in hardware between all of these three elements, we can make sure that those kind of attacks can be prevented. And then there's other masking and isolation for GPIOs and interrupts and security wrappers around the other bus masters in the system, and then locking this all down securely.
Okay. So, Brendon, can you tell me some more about the other parts of this secure execution environment?
Yeah, so coming back a little bit more detail on that list, I ran through quite quickly. So secure boot. So secure boot, again, is, am I running legitimate software? By having the device boot out of its own ROM, that's immutable, right? It cannot be messed with because it's burnt into the device, basically.
Right.
So what we do inside the ROM is have the ROM look for establishing a chain of trust. So it does that with root of trust keys and boots when it's receiving information to boot from, where it has an image it's trying to boot from somewhere else. It can establish a chain of trust with that image by validating the certificates and so on. Also supporting encrypted images so that you can receive an encrypted image and you can handle it and then know that that source code has not been messed with because it's encrypted. Secure primitives, we talked about that as well, just briefly. So here's some illustration of some of the key hardware accelerators that you typically need. Now, I mentioned much earlier about Casper, just to round that out a little bit. Casper is another coprocessor. There's some pretty heavy lifting math in some of these encryption algorithms like ECC. So
Yeah.
Casper puts in a bunch of hardware acceleration. And this makes a big difference to system performance, right?
I bet. Yeah.
Yeah. If you're trying to establish a link, a secure link, these things can take a lot of processing time and burn
Right.
power.
Another important element of securing our systems is storage, right, Brendon?
Yeah, of course. So those key secrets in the application. Yeah. So secure storage, securing your information, and also as part of that, securely storing keys that we use in multiple things like booting. So in these parts, we have this SRAM Puff technology. And I was going to make a corny joke about Puff the Magic Dragon, but I'll avoid that because I think Puff's known enough. I know you know a little bit about Puff yourself,
I
right?
do indeed.
But this helps us. I'll talk about that a bit more in a moment for the people listening who maybe don't know Puff so well. But along with that, there's also, we're storing stuff somewhat securely. We have keys, they're securely stored, but being able to decrypt things on the fly. So decrypting our actual executing application code on the fly offers a good level of protection, right? Because people can somehow get to an external flash device, download the code, and then start just knife and forking their way through it because it's encrypted. And we can also encrypt it per device as well. So that even makes things more secure than that. And then encryption, decryption of the valuable application data with something like AES encryption. I know you're an expert on this, Amelia.
Well, I know a bit about it. I'm not an expert.
Well, I know you've spoken to our good friends at Intrinsic ID, from whom we've got this SRAM Puff technology. So Puff is a technology that was invented a few decades ago, but Intrinsic ID have added a lot of extra security around it. We use a hardware implementation of their technology using their QWIDI key IP, and this provides hardware unique key that's tied exactly to that one. So this provides a hardware unique key that's unique to each device, and it does that using process variation. So when an SRAM boots up, it will have a unique signature of ones and zeros on that particular SRAM.
Yeah.
And if you make the SRAM big enough and add the right processing around that to ensure you can recover that signature, then you have a very, very robust and extremely hard to break unique signature. And that can be used to generate other things like AES keys and device keys and so on and so forth. Now, one of the really cool things about this is you turn the power off, key's gone. You can't read the key. There's no way software can go and read that key.
Yeah.
It's impossible on this part. So it's incredibly difficult to intercept that. So it's a very robust technology.
Okay, so let's talk a little bit more about this secure execution environment. What else do you got?
Yeah, just to round out the other items on the list, secure update, we touched on a few times there. I think one of the key things to note about this is, again, how do you enable the software to be updated? So you're going to write it to a flash somewhere, and this device obviously has on-chip flash, has ECC on it as well, by the way, which I didn't mention before. But we provide these in-system programming commands as part of the ROM. So again, they're immutable. You can't go in and hack them. And that supports OTA. So once you establish the root of trust back to the device that's giving you the update, then it can send this encrypted image over to you, and you can use these safe function calls to go and update the flash. And that's what the in-system programming enables. During production time, you can use that same thing to protect your IP for those people who want to make clones of your product. Stop them. And then finally, secure debug. This is a cool thing that comes with Arm v8M. So you can decide what access you want to give different people for debug at different points in the life cycle.
Oh, okay.
Yeah, so you can start with a part that's completely unlocked, and you can then, using certificates that you put in during provisioning, during programming in production, you can enable access, say, to the whole system with one certificate, or just to the non-secure part of the system and with a different certificate, or not at all. Say for an end user using some kind of appliance or something, they wouldn't get any kind of access without the certificate. And it even goes all the way to an RMA. So if the customer can design with us, they think there's some issue with the chip, they can actually give us a certificate so we can get enough access to do RMAs on the chip without them exposing any of their IP to us. It's a pretty complete solution for the entire life cycle of the device.
Okay. Now, Brendon, what does the software situation look like for this system? Does it fall in line with your MCU Espresso software environment we talked about in a previous Jock Talk?
Yeah, I know I've been over this with you a couple of times. And,
Yes.
and our beloved listeners who love to listen to Brendon and Amelia will know about MCU Espresso, and it is consistent with that tool suite, which is good news for everyone using our devices. And so there's the standard IDE, SDK config tools. We obviously add examples for the SDK for the security features of the parts. They're available in the SDK today. One thing we're augmenting our config tools with is our trusted execution environment configuration tool. If you remember, there's all these attribution units in the part. You can imagine if you're just poking registers and you think, what, did I line that one up with this one? And that can get very difficult very easily. And if you get that wrong, you can end up causing hard faults in the system, which are hard to debug. So this is one screenshot from the tool. There's a few different views depending on what you're doing, but I'm intending to show you here how you can get a view of what's accessible by which type of environment. In other words, from the secure or non-secure environment, what devices are mapped into each of those regions, and if there's any errors or conflicts. I'm not intending to try and give you a demo of this. It's just to give an illustration of a nice visualization we're offering our customers, and that comes out in our next tool release in June. So yeah, that should help.
Okay, so what else is on the horizon for the LPC5500? Anything cool you can talk about?
Yeah. So it's got everyone excited about this now. So this is what we're starting off with, the first part that we've launched into the market in Q1, and that's the LPC55S6X family. Then we will have our next round of parts coming, which will be a lower cost variance of that family. And that's the 55SX family. And also we will have parts which don't have TrustZone for people who they don't need that level of security. They're more concerned about, they have parts that maybe aren't remote connected and so on, and they need a lower price point. That price point reduction will continue down to devices in the 551X family, even down to a flashless device later. So those lower end parts offer less flash, so more cost optimization there. CAN FD will be coming in some of those parts as well. And then at the other end, we're adding some higher memory footprint devices and more clock speed, enabling a broader range of applications such as HMI at the top end of the family.
Cool. Okay. So Brendon, if I want more information, where should I go?
Yeah, so the device series information is up on NXP.com today, so you can get lots of information about the LPC5500 family. Data sheets, user manuals, the boards are available to order as well. And then the devices are supported in our SDK. You can download our MCU Expresso tools in the usual places, and our community is active there too as well. Mouse have did a great job collecting up a bunch of NXP videos about the device series. So actually, they give us a nice convenient point to see their point of view and also several NXP videos as well.
Excellent. Well, I'm going to click that link and go to a Mouser page for more information. Brendon, I think that's all I have time for today. Thank you so much for joining me.
Great. Thanks for your time, Amelia. Talk to you next time.
And before we go, you didn't forget to click that link, did you? There you can find even more information about the LPC5500 family of MCUs from NXP. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. Can't miss it, it's right across the top. Or head on over to YouTube. Keyword